let's solve some more questions from the chapter Conduction. And this will be our third video on this chapter, and this will be the last video. Okay. The first question is from the resistance circuit diagram. The question is an ice box made of 3 centimeter thick styrofoam whose thermal conductivity is 0.033 watt per meter degree Celsius have outer surface area as 0.4 meter square. Okay. Uh, just a minute. I'll have to change this again. Yeah. So the outer surface area is 0.74 meter square and inner surface area is 0.5708. Okay. So this is AI and let this be AO, A naught. Okay. Initially, the box is filled with 50 kilogram of ice at 0 degree Celsius. The mass of ice is given. The initial mass of ice. This is not M dot. This is MI actually. So this is initial mass of ice, which is 50 kilogram, and the initial temperature is 0 degrees Celsius, and the inner surface temperature of the ice box is to be maintained at 0 degrees Celsius all times. The heat of fusion of ice at 0 degrees Celsius is 333.7 kilojoule per kilogram. This is the data given. It is kilojoule per kilogram. And the heat transfer coefficient between the outer surface of the ice box and the surrounding air at 28 degrees Celsius is 18 watt per meter square degree Celsius. Okay. So they have asked us how long it will take for the ice in the box to melt completely in hours. Okay. So this type of question we have done in the second video, that liquid nitrogen boil off question. That question was based on the same concept. So let's draw we draw a schematic diagram. This is the ice box, 50 kg ice at 0 degree Celsius. Okay, and inner surface is given. Inner surface is 0.5708 meter square, and it is actually insulated by 3 centimeter thick styrofoam. Okay, so this outer surface is 0.74 meters. Okay, and T infinity, that is surrounding temperature, is 28 degrees Celsius, and H is 18 watt per meter square degree Celsius. Okay, so what can we analyze from this question? That heat from the surroundings will go into the box and will melt the ice. Okay, so let's draw its resistance circuit diagram. It will be the convective resistance offered by the ambient air, which will be equal to 1 by HA, and then the conductive resistance offered by the box of ice. Okay, and this will be 0 degrees Celsius, this temperature, and this temperature will be what it will be? It will be 28 degrees Celsius. Okay. So we can find the heat transfer rate by using all this data. Okay, let's find the heat transfer rate. So Q will be delta T by R total. Okay, and delta T is equals to 28 minus 0, and R total will be R conductance plus R convection. Okay, so this is 28 upon L by Ka plus 1 by Ha. Okay, so when you put the values, what are the values that have been given? Yeah, so this conductive resistance will be offered by this box, okay, which is 3 centimeter thick. This is styrofoam, 3 centimeter styrofoam. Okay, so this is 3 centimeter, that is 0.03 meter, and K is what? K is 0.033 watt per meter degree Celsius, and area. So here area will be inner area. Okay, this area. Yeah. So this value is equal to 0.033 This is AI, and this is equal to 0.5708 meter square. Okay. H is equal to, again, it is equal to 18 watt per meter square degree Celsius. And here, area will be outer surface area, because this area is in contact with the ambient air, this area, outer area. Okay. So this value is equal to 0.74. This is 0.74. Okay. So you can find the heat transfer rate, which will be equal to, this will be equal to, yeah, so it is 16.79 watt. Okay. That means joule per second. That means 16.79 joules of heat is going into that box per second. Okay. What is the question? The question is how long it will take for the ice in the box to melt completely in hours. Okay. So now we need to find the required heat to melt all of this ice. So this will be mass of ice into its heat of fusion. That is 333.7 kilojoule per kg. So this will be in kilojoules. Okay. So heat required to melt all the ice. Heat required to melt all the ice is 50 kilograms into 333.7 kilojoule per kg. Okay, this is in kg. This kg gets cancelled out. Q required comes out to be, this is a big number, which is 16685,000. And this will be in joules, I guess. Yeah, the value is written in joules. Okay, do the calculation. So this is the required heat, and this is the heat that is coming into the box per second. Divided Q required by Q. This will give you time in seconds, because here it is in joule per seconds, here it is in joule. So joule and joule will get cancelled out, and you will get the answer in seconds. Okay, divide this answer by 3600. Divide this answer by 3600, and you will get the answer in number of hours. The answer is 276 hours. Okay. So this type of question, we've done it in the second video also, and this was all from this question. Next is the question from conduction with heat generation. Heat is generated uniformly in a 4 centimeter diameter, 12 centimeter long solid bar. Okay, so this is 0.04 meter diameter and 0.12 meter is its length. Thermal conductivity is given. The temperature at the center and at the surface of the bar are measured to be 210 degrees Celsius and 45 degrees Celsius respectively. The rate of thermal energy generation within the bar is in watt. Be careful, you have to fill the answer in watt. Okay. So I have actually derived this formula in the second video. I've told you that by using governing heat conduction equation of cylinder, you can actually derive the formula which we have used in the previous video also. I've derived the formula for sphere. Okay, but you know the boundary conditions, they are the same. So the governing heat conduction equation for cylinder is 1 by R del by del R R del T by del R plus Q dot G by K is equal to 1 by alpha delta T by delta small t, which is time. Okay, you solve this, put the boundary conditions, and you get the formula as Tc minus Ts is equal to Q dot G. This is R square by 4K. In case of sphere, it was 6K. Okay, Tc is center temperature, Ts is surface temperature. So we have derived this formula in the previous video. Okay, now you have to find the rate of thermal energy generation within the bar in watt. But in this formula, the heat generation is in watt per meter cube. This was the important part. So Tc is 210 degrees Celsius. This we know. Okay. TS is 45 degrees Celsius. Great. Radius is 0.02 meter because diameter is given. So be careful, the diameter is given, and here in the formula it is radius. And thermal conductivity is also given, which is 2.4 watt per meter Kelvin. Okay, here it is meter. So R will also be in meters. This is 2.4 watt per meter Kelvin. Okay. So you will get Q dot G, Q dot G in watt per meter. Okay, when you solve this, you get Q dot G, that is heat generation per unit volume, and its value will be it's a big value, 3960000 watt per meter. Okay, so what you have to do to find the rate of thermal energy generation in watt, multiply this by its volume, by the volume of the cylinder, and you will get Q in watt. Okay, let's do it. I'll have to rub it, I guess. Yeah. So let's rub this portion. So Q dot G, that is heat generation per unit volume, is equal to 3960000. If I multiply it with volume, this will be in watts, and this becomes capital Q. I denote it by capital Q. Volume is pi by 4 d square L. D is 0.04 meter, L is 0.12 meter. Put all the values, get Q as 597.153 watt. Okay. So this is your answer. So it is important to learn these formulas for sphere as well as cylinder. This formula. The next question is again from the resistance circuit diagram. The lining of box type furnace is made of a refractory layer and steel plate as shown in the figure. The figure is not there. So let me first draw the figure for you. This is refractory. Okay. And this is steel. Okay. So this is 1273 Kelvin, and some data is also given. This is at 473 Kelvin. This is furnace, and this is ambient. Okay, and some data is also given that this refractory thickness is 8 centimeter, 80 mm, that is 0.08 meter, and the thickness of steel plate is 4 mm. So this is 0.004 meter. Okay, and the thermal conductivity of refractory is, some data is missing in this question. This is 1.2 watt per meter Kelvin, and the thermal conductivity of steel will be more than this refractory, which is 32 watt per meter. Okay, so now this is the complete question. Okay. The steady state temperature at the surface of the refractory is 1273 Kelvin, and that at the outer steel surface is 473 Kelvin. If the steady state heat flux through the refractory steel plate composite is 1600 watt per meter square. Okay, flux is given, that is Q double dash by is equal to Q by A is 1600 watt per meter square. This is given, and heat flow is along x direction only. This is x direction. The thermal contact resistance meter square Kelvin per watt. Why is this unit meter square Kelvin per watt? It should have been Kelvin per watt only, because here flux is given. When you will balance the units, you will get this unit. Okay. If you were given only heat transfer rate in watt, then the units would have been Kelvin per watt. Okay. So the contact resistance you have to find. Okay, very simple, very basic question. Temperature difference is given, flux is given. All you have to draw is the resistance circuit diagram. Get the answer. So the resistance circuit diagram will be no heat transfer coefficient is given. So we will assume no convective resistance here. Okay. So this is conduction resistance offered by refractory. This is contact resistance, and this will be conduction resistance offered by steel. Okay, so this will be L by Ka. Okay, L1 by K1 A1 whatever you want, A only, and this will be Rc, and this will be L2 by K2 A. Okay, so the data is given to you. L1 is given, K1 is given, L2 is given, K2 is given, Rc you have to find delta T. This is 1273 Kelvin, and this is 473 Kelvin. Let's see if I have the next page. No. So yeah, this is 473 Kelvin. Okay. So Q is equal to delta T by R total. Basic equation. R total will be R conduction plus R contact, R conduction by refractory plus R conduction by steel plus the contact resistance, because they all are in series, so they will directly get added up. So this will be R total, and delta T is 1273 minus 473 Kelvin. So let me remove this figure. Yeah, make space for something. Okay, so this will be delta T will be 1273 minus 473 upon L1. L1 was 0.08 upon K1. K1 was, I guess it was, let me check that, 1.2 plus RC plus this is 0.004, the thickness of the steel plate. This was 32A. Okay, what you do is you take A common from here, and when you take A common from here, and A automatically comes here. Sorry, and A automatically comes in this part also. Okay, that is why the units are in meter square Kelvin per watt, and A comes here also. Okay, so this is RC in this term also. Okay, take this A here. That is why the units are meter square Kelvin per watt. Okay, so now you can solve this question. Q by A is given to you 1600 watt per meter square. And 1273 minus 473 will be 800. Solve this, and I guess RC will be equal to uh, 0.433 meter square Kelvin per watt. This will be the answer. Okay, so when you take A common from here, if you multiply A here and A here, okay, so this A goes here, and this A is left here. So the units of area are meter square, and that is why when flux is given to you, heat flux is given to you, the units of contact resistance will be meter square Kelvin per watt. Let's move on to the next question. Okay, the next question is again based on that center temperature and surface temperature. The center to surface temperature difference in a heat generating cylindrical rod of diameter 8 cm is 30 degrees Celsius. This is the data. Under similar conditions, the center to surface temperature difference in case of sphere of diameter 8 cm is. Okay. So if you now don't remember the formula, this will be a very lengthy question for you. But now I've told you to remember the formulas of this, this center temperature, the difference of the center temperature and the surface temperature in case of cylinder is Q dot G R square by 4K. This is for cylinder, and temperature at center minus surface temperature for sphere is Q dot G R square by 6K. This is for sphere. So as I have asked you to remember these formulas, this question will now be very simple for you. Very simple for you. Okay. So divide it. Okay. This we know. This is 30 degrees Celsius. QG and QG gets cancelled out. Why? Because under similar conditions. So K also gets cancelled out. Diameter 8 centimeter, diameter 8 centimeter. R square also gets cancelled out. So 30 by TC minus TS is equal to, this is 6 by 4. That is 3 by 2. Okay. This gets cancelled out 10. So this temperature difference for a sphere, this is for cylinder, this is for sphere, comes out to be 20 degrees Celsius. Okay. So if you were to follow the conventional method, it would have been very long question, but as we remember the formulas, it's very simple. The next question is again based on conduction with heat generation. A wire whose resistance per centimeter length is 0.1 ohm. The resistance per centimeter length. So I will make it, first of all, I'll make it in meters. Okay. Because I like to work in SI units, and so should you. And also the thermal conductivity has been asked in watt per meter Kelvin. So it will be beneficial for us to work in SI units and to convert this in meters. So resistance per centimeter length is 0.1 ohm per ohm. That is resistance per centimeter length is equal to 0.1 ohm per centimeter. This will be L. Okay. So convert it. 0.1 ohm. 1 centimeter is equal to 0.01 meter. Okay. So this is 0.1 divided by 0.01 meter. That implies this is 10 ohm per meter. What is this? This is R by L. Okay. Do not forget this thing, that it is resistance per unit length is given. Per unit length is given. Okay. Is embedded along the axis of a cylindrical cement tube of radii 0.06 centimeter and 1.2 centimeter. 1.2 centimeter. Okay. So the outer radii of this cement tube is 1.2 centimeter, and the inner radii also given. So let this be Ri, and this is R naught. Okay. R naught is 1.2 centimeter. That is 0.012 meter, and Ri is 0.06 centimeter. 0.06 centimeter. So that is 0.06 into 10 raised to minus 2 meter. Okay. A current of 6 amperes flow in the wire to keep a steady state temperature. Temperature difference of 130 degrees Celsius between the inner and outer surfaces. Okay. The thermal conductivity of the cement is. Okay. So can I say that the heat generated by this wire, when it is kept inside, when it is embedded along the axis of the cylinder, this axis which is going inside, the heat generated in this wire will actually be the heat conducted through this cylindrical shell. Okay. This was the concept. So heat generated in the wire will be equal to Q dot is equal to I square R. I is 6 ampere. So that is 36 into 10. This is ohm per meter. Okay. So this will be equal to 360 watt per meter. Okay. So basically this is Q dot by L. Okay. this is basically Q dot by L, or we simply write it as Q in subject of heat transfer. This basically denotes rate of heat transfer only. So Q by L is 360 watt per meter. Take care of the units, okay? So this is actually conducted by this cylindrical shell, and Q will be again equal to delta T by R total. We have the page or not? Yeah. Q is equal to delta T. Delta T, the temperature difference is given to you between the inner and outer surface is 130 degrees Celsius. So this is 130, and total conduction resistance for a cylindrical shell is, you know the formula, that is ln R2 by R1 upon 2 pi K L. Okay, you have to find the thermal conductivity in watt per meter. So take this L there. That implies Q by L is equal to 130 upon ln R2 by R1 upon 2 pi K L. Sorry, 2 pi K. Take an L here. Now Q by L is, you know this Q by L. So that is why I emphasize on following or following this unit part very carefully, because units play a very important role. Okay, so this is actually watt per meter, and this is actually Q by L. From here, you can directly put Q by L. So this is value is 360. So 360 is equal to 130 upon ln R2 by R1. This is a ratio, so it doesn't matter whether you put R in centimeters or meters. Put R2 by R1, put R2 and R1 in centimeters only. R2 is what? R2 is 1.2 centimeter, R1 is 0.06 centimeter. So this is the data correct? This is 0.06. Let me just confirm it. There is a question. It is, yes, it is 0.06. So R2 is 1.2, this is 0.06, and upon 2 pi K. Find K from here. Okay. K will be equal to, implies K will be equal to, the answer of K will be, I don't know the answer. Whatever be the answer, I can tell you the answer. Just a minute. Okay. So K comes out to be 1.32 watt per meter. Solve it, you get the answer. 1.32, that is, okay, so this is a question with options, that is B. B answer. So B is the answer. Next question is a mild steel tank of wall thickness 12 mm. Wall thickness is 12 mm, that is L is 0.012 meter. Contains water at 95 degrees Celsius. The thermal conductivity of mild steel is given, and the heat transfer coefficients for the inside and outside the tank are 2850 and 10 watt per meter square degree Celsius respectively. If the atmospheric temperature is 15 degrees Celsius, what you will find, then the overall heat transfer coefficient is, okay, the options are given to you. Then the overall heat transfer coefficient, I think I have already told you the concept of overall heat transfer coefficient in the first video, and I told you that whenever this question is asked of the overall heat transfer coefficient, use this. UA is equal to 1 by R total. Okay, the total resistance that is offered in the path of heat transfer. Okay, so UA is equal to 1 by R total. Okay, so this is the wall. This is the wall. The thickness is 0.012 meter. Okay, the temperature of water is 95 degrees Celsius, and the atmospheric temperature is 15 degrees Celsius. Great. The heat transfer coefficients for the inside is 2850 watt per meter degree Celsius. Let this be H1, and for outside it is H2, and the value is equal to 10 watt per meter square degree Celsius. Okay. Now you can draw the resistance circuit diagram, which is This temperature is what? This is 95 degrees Celsius. Convective resistance, which is 1 by H1A, and the conductive resistance by this steel wall. So this will be LS by KSA, and area will be same, So this will be convective resistance on the ambient side, which is 1 by H2A. Okay, so you can find the total resistance, which is our total is equal to 1 by H1A plus LS by KSA plus 1 by H2A. Okay, let me remove something. So now UA is equal to 1 by R total. Okay, so put this R total here. This A will get cancelled out by this A, and you will directly get the value of E. We put the values. H1 is this 2850, H2 is 10, KS and LS is given to you. LS, the length of that steel wall is 0.012 meter, and thermal conductivity is also given, that is 50 watt per meter degree Celsius. So you know all the values, get the answer of you as the answer will be, I don't have the answer again, so let me check the answer. This is 9.94. Okay, the answer is 9.94 watt per meter square degree Celsius. That was again a simple question. This is the next question is from the application of Fourier's law, and the question is the temperature distribution across a large concrete slab 500 mm thick heated from one side. This is L is equal to 0.5 meter heated from one side as measured by thermocouples approximates to the following relation. So this temperature distribution is given to you now, where T is in degree Celsius and X is in meters. Considering an area of 4 meter square, thermal diffusivity is given to you in meter square per hour. The maximum rate of change of temperature in the slab is. Okay. So now the governing heat conduction equation for plane slab. We have studied this equation for the sphere, for the cylinder, and now it is for the plane slab. This is del 2T by del X square plus Q dot G by K is equal to 1 by alpha delta T by del small. Okay, this is in watt per meter cube. This is thermal conductivity, temperature, time, and this is distance from one end, generally measured from one end. You can take it from center also, but I'm taking this as reference, so this will be mixed. Okay, so this is just the distance from the reference, from the origin. Whatever you can take this. Okay, this is del T by del small. So there is no heat generation in the wall, so this term becomes 0, and the equation reduces to uh, del 2T by del X square is equal to 1 by alpha del T by del small. So they have asked us to find maximum rate of change of temperature. Maximum rate means time change of temperature. So you have to find this term, that is del T by del small t. Okay. So this will be maximum only if this is maximum. Correct? From the equation, if this is maximum, this will be maximum. Okay. So now let's find out del 2T by del X square. How we can find this out? We have the temperature relation with X, and which is some equation is given to you, and directly differentiating it. So partially differentiating it with x, the equation is 120 minus 100x. So this will be minus 100 plus 24 into 248x. Okay, and 120 plus 120 x square, and this will be 30 into 4, that is again 120 x cube. And second partial derivative with respect to x will be equal to, this will be 0, so this will be 48 plus 120 to 40x and minus 360x. So this will be del 2t by x square. Okay, so now we have to find the value of x where this del 2t by del x square will be maximum, because if this is maximum then this will be maximum. So consider this as a function fx. Okay, so fx is equal to, function is 48 plus 240x, 48 plus 240x minus 360 x square. Okay, so to find where it is maximum, we have to just differentiate it with respect to x. This will be 240 minus 360x, that is 720x, and put it equal to 0. X is equal to 1 by 3. Now if you double derivate it, it will actually show you whether at x is equal to 1 by 3 this function is maximum or not. If you get the negative value, then this corresponds to the maximum value. Okay? So f double dash x is equal to 240 minus 720x minus 720. Great. So this is the negative value. That means x is equal to 1 by 3 will correspond to the maximum value. Now put x is equal to 1 by 3 in what? This equation, this function. This is fx or del 2t by del x square at x is equal to 1 by 3. So this equation is 48. 48 plus 240, this is 48. 240 1 by 3 minus 360 1 by 3 square. Okay, you will get del 2t by del x square is equal to, the value is 88, I guess. Yes, it will be 88. Let me check this, not sure. Yeah, this is 88. So this is 88, and 88 is equal to 1 by alpha del t by del t. Check the units. This is in meter square per hour. Right. Meter square per hour, and you have to find the answer in degrees Celsius per hour only. So there is no problem. So 1.77 into 10 to the minus 3. Put alpha is equal to 1.77 into 10 to the minus 3. And you will get the answer as 0.155 degrees Celsius per hour. Right. This will be delta capital T by delta. Yeah, this is the answer. Let me confirm it. Yes, this is the answer. So this is the answer. So with this, we have completed the chapter conduction. I guess we have solved a lot many questions from this chapter. So what you do is, whenever you see a question, first try to solve it yourself and then see the solution. Okay. So these are some questions from conduction. We'll move on to the next chapter in the second video. Okay. Thanks.